Hello, if you can hear me, then just let me know so that we can get started. I'm starting. All right, ladies and gentlemen, good afternoon, and this is Miracle Chibuzor Marcel. I'll be delivering lectures on black holes today. So just like we have been doing before. So I'm the founder and the director of Pan-African Citizen Science eLab, an organization based in Africa for the promotion of citizen science in Africa. So in the previous lectures, we delved into first series on stars, second series on stars. So today we are going to be studying black holes. I mean, third series on stars. We're going to be talking about black holes. So from the table of contents, I'll be introducing black holes. I'll be explaining what black holes are. I'll be revising I'll be revising our previous knowledge on stellar life cycle to understand where black holes are coming from. Then I'll talk about types of black holes. Then I'll talk about black holes and space-time. Black holes are going to help us to understand space-time fabric. Then I'll talk about Hawking radiations. I will say all sorts of things in between these topics anyway. So, what is a black hole? A black hole is a region of space-time where gravity is so strong and that nothing, not even light, in fact, all electromagnetic waves can escape. Do you understand? Okay, it's capable of escaping because in physics we take light as the entity that has a faster speed. Okay, nothing can be faster than the speed of light. So So this occurs because a massive amount of matter has been compressed into a very small area, creating a singularity at the center surrounded by an event horizon. Beyond which nothing can return. So I'm going to explain all of these things as we move on. So first of all, let us revise so that we can refresh our memory on life cycle of stars. Remember in the first series of stars, I described the formation of stars, how stars are formed. And I said that stars are formed from uh, the collapse of the giant molecular clouds, okay? So when that happens, those, the giant molecular cloud becomes a protostar, and from there it migrates to a proper star. Now, depending on the starting mass of the star, it could be a small star, okay? It could be a large star. But for the sake of a black hole, which we want to study today, we're going to focus on large stars, okay? The progenitor stars that give rise to black holes are usually very large, okay? So when they become a large star, they become a main sequence, they fuse hydrogen and all of those nuclear fusion mechanisms that happen at the center takes place for millions of years. So if you want to understand what is going on there, I described it fully in our first series lectures. So I'm just giving a summary of what is going on inside the stars. So then it becomes a red supergiant. After that, it explodes into supernovae and forms a black hole. Look at the arrow. It forms a black hole. So these large stars can also form neutron stars. Okay, but if the starting mass, the main sequence star mass of this star is above 20 solar masses, it will definitely collapse to a black hole. So we shall see when it collapses to a neutron star in the future. But for today, we want to talk about black holes. So to understand black holes, you need advanced mathematics. You need general theory of relativity. Okay, you need all kinds of relativistic equations to understand a black hole. And we are not armed to, at this lecture, I'm not going to focus on all of these things, okay, because you need to have advanced mathematical skills to be able to understand these equations, these scary equations. Oh, sorry for the interruption. Let me get my slide. To understand a black hole fully, to understand a black hole, we need to understand the idea of escape velocity. So on the screen, we have this escape velocity. So what is escape velocity? Escape velocity must attain to be able to break free from the gravitational pull of a planet, moon, or star without any further. Okay? So if you want to throw an object to escape the Earth's gravitational pull, that minimum speed that you should exert of that object to be able to break free from the Earth's gravitational field, or not just the Earth, the moon, or any celestial body, that speed is. So, and I use this simulation to describe escape velocity. So here is a cannon. Okay, it shoots a cannon. The cannonball falls back. It shoots it again at a higher speed. It came back. Okay, then it shoots it at even a greater speed, and the cannonball did not return. So you see that? So it's a minimum speed. So every object in through which, if you throw an object in it, it will not return again. So even light has a speed. Like I told you, the speed of light is the fastest speed in the universe. Okay, so here is a man flashing a torch. Okay, so the speed of light is high enough to escape. Torchlight through the sky at night, it is actually leaving Earth. In fact, if you flash it on the moon, it can even reach the moon. But the only thing is, you may not be able to notice it because the moon, even the intensity of your light is not strong enough to be noticed. But believe me, whenever you point something, a torchlight to the sky, maybe a laser enough to leave Earth. But bullets are not. If you shoot a bullet into the sky, it will never leave the Earth. So here is the table describing the escape velocities from different celestial bodies. Planets in our solar system. So the first column is the celestial bodies: the Mercury, Venus, Earth, Mars, Jupiter, Saturn. Okay, I even put the sun there, and then all the way to the neutron stars. Then I gave their escape velocity in kilometers per second, and then I gave it in the units of meters per second. You understand? So look at it here. Then I also drafted their equivalent to the speed of sound so that it can help us to understand. The speed of sound is about 343 meters per second. 343 meters per second. So if we say that something is moving at 2 times the speed of sound, you should be able to understand, have an idea of what we're talking about. I know sound is very fast, okay? And here in this column, I gave the value in the speed equivalent to the speed of light, okay? So on Mercury, if you want to escape Mercury, you would need a speed that is at least 12 times the speed of sound. If you are on Venus, you need a speed that is about 30 times the speed of sound. If you are on Earth, our own planet, you need a speed that is at least 32 times the speed of sound. Has attained this speed yet, except rockets. That is why we only use rockets to send things out of Earth, whether satellites or astronauts. We send objects with this amount of speed, 32 times the speed of sound. So it is an enormous speed, okay? Then we have Mars. Mars by 14 times the speed of sound. Jupiter, okay? Now, as the object sorry for the interruption. Let me bring up my slide. So as you go down the column, this minimum speed increases, and the reason is because the masses increases. So if you look at the sun, if you want to escape the sun, you need about 1,800 times the speed of sound. Now, how about the white dwarf? I haven't explained what the white dwarf is, okay? But the white dwarf is a dead star. It's almost in the class of a black hole, but it is a very dense, remnant of a star. If you want to escape it, you need about 17,000 times the speed of sound. How about a neutron star? You need about 349 times the speed of sound. In fact, you can even equate to the speed of light, which is 0.4 times the speed of light. Okay, so if you have a black hole, what speed can you escape from a black hole? At what speed can you escape from a black hole? So to understand it, from this idea I'm about to explain. So this equation here is an equation of an escape velocity. So the escape velocity states that it is equals to the square root of 2gm over r, where g represents the gravitational constant. Is a constant. 2 is a number. Mass represents the mass of the star. M represents the mass of the star, and R represents the radius of the star. So from here to the outermost part of the star. Okay, that is just the radius. Okay. Now I want you to go with me. Assuming you are on top of this star, okay, you are just standing here. Maybe you are an astronaut or an explorer or even light itself. You want to escape from the star. You can escape, okay, with a particular speed called the escape velocity. If it were the sun, you should have about 1,800, okay? That is times the speed of sound. Now, imagine now that we begin to shrink this star. Okay, let's just imagine that the support, like I told you, to support a star, there has to be fusion in the core. To support the weight of the star, there has to be fusion in the core. Okay, so now imagine that the fusion is over. The fusion is cut off. The star could not support itself again. It is going to collapse. So now this star, let us make it to collapse slowly so that we can understand what is going on. So as this star is collapsing, the radius is getting smaller. So from this equation, if this radius is getting smaller, you would, insinuate that the escape velocity is going to what? Increase. So it gets higher and higher and higher. So this huge mass is going to shrink and shrink while the escape velocity increases to such a point that a point comes where we cannot even see the light again. It becomes a black region. So we call that a black hole. So here is the diagram. Okay, here is the black hole. And here is the sketch I made on my whiteboard. Okay, so we have been able to shrink all of this mass into this singular point. All of this mass now are now in a singular point. Okay, very, very tiny point. In fact, we can't even use tiny to describe it because it is more tinier than the most tiniest of things in the universe. So that is how we're able to compress this star. Okay, and because of that, the region around here, the gravity around the region around here is so enormous that it can't allow light to escape. Sorry for the interruption. So the region around here, the gravity is so enormous that light can escape. Okay, because of the enormous gravity. So if at all you want light to escape, you would need a speed that is higher than the speed of light. We don't even know the value, but it should be higher than the speed of light. And like I told you before, light is the fastest speed. Light is the fastest speed in the universe, and nothing can be faster than the speed of light. So ultimately, nothing can escape this region. Okay, so if you are at this edge, so this edge is described here. If you are at this edge, remember that this edge is not the surface of the star. Remember this. This edge here, I have not described what it is called yet. This edge here is not the surface of the star. All of those stars has been compressed into this tiny part. This here is just the region surrounding this point. Understand that, okay? This region here, this black region is surrounding this point. Do you understand? So So here is not the surface of the star that we were standing on top before. But you are here. But this region is completely dark because of the enormous gravity coming out from this singular point. Okay. However, if you are here, you can escape at the speed of light. That if you are outside that region, you can escape at any arbitrary speed. Okay, depending on how close you are. Okay, you can escape at any arbitrary speed that is less than the speed of light. So that is exactly the idea of a black hole. So black hole is just a region that is not allowing, the gravity is so enormous that light cannot escape. So it becomes dark. It becomes black. So a black hole is an ideal definition of a black body. It's an ideal definition of a black body. So now, in describing these different parts that I was talking about before, so that region here is called the event horizon. No, I didn't mention the name before. This region here is called the event horizon. Okay. Now, that single point where all this mass has been compressed together is called the singularity. We call that the singularity. So from now on, I'll call it the singularity. I'll not call it the point. I'll call it a singularity. Then from this singularity to this event horizon is called the Schwarzschild radius. This is the name of a man that came up with this mathematical model. Okay, the Schwarzschild radius. So know these three parts: event horizon, Schwarzschild radius, and the singularity. So let me go back to this picture. So here is the singularity where all the matter, all the mass is being compressed. So here, so from this point to this point is called the Schwarzschild radius, not just the radius. We call it the Schwarzschild radius. And this circle here is the event horizon. So in this picture, you may not be able to see the singularity and the Schwarzschild radius. You can only see the event horizon, but just know these definitions. So here is this is another way of describing. This is if you are observing the space around a black hole from another perspective. Okay, so here is the event horizon. Okay, so here's the singularity. So this singularity, how big is this singularity? In physics, there's something we call the Planck's length. It is the Planck's length is the minimum size an object can get. Have you ever asked yourself, if you break an object and continue breaking it, even break it to the point of an atom, you know you can continue breaking it into some of these subatomic particles. Okay. Now, if you continue breaking it, there's a point you can no longer break these materials. So we call that the Planck's length. So Planck's length is the smallest size an object can be. Okay. Now, and I'm telling you right now that even this singularity is smaller than the Planck's length. Do you understand? So a singularity of a black hole, kind of invades our understanding of physics. Everything that we know about physics is even smaller than the Planck's length. So what could possibly become smaller than the Planck's length? How could you compress all of this mass here to a size that is smaller than the Planck's length? And it is still there because we can feel it. It has not escaped. It has not left the universe. It is still there because we can measure the mass of a black hole. So it makes you to wonder that that a black hole is very mysterious. So coming back to that terminology that I gave you before, I said event horizon. The event horizon simply means the boundary of a black hole from within which nothing can escape. Then I said a Schwarzschild radius is the radius. It's the radius to which a given mass must be compressed for a non-rotating black hole. Also, the radius of event horizon from a non-rotating black hole. Although most of the things I'm describing here is ideal, okay? We are using a non-rotating black holes, okay? But most black holes rotate, but for simplicity, we use non-rotating black holes. How about a singularity? So a singularity is a mathematical point of zero volume associated with infinite values of physical parameters such as density, okay? So this singularity is actually, it's a region, it's a point of zero volume, okay? So if you imagine the formula of density is mass over volume. So that means density is inversely proportional to the volume. If the volume becomes zero, it means that the density becomes infinite, okay? And that is very wrong. So because of that, all known laws of physics break down at this singularity. All known laws of physics, all quantum mechanical laws, all Newton's laws, all the laws of physics that we know of today break down at this singularity. And that is why we can say that a black hole is the object that has the most density in the universe. Okay, we can't say that because even the physical processes that happen, we don't even know how it is going to happen at the singularity. So you don't say that that a black hole has the most density in the universe. So, however, we came up with another way of describing the density of a black hole. So astronomers have another way of defining black hole density. So we use what we call the average density. We use average density. So here is the formula. It is from just the basic formula of a black hole, of an object. Sorry, the basic formula of density, which is mass over volume. So we can get the mass of a black hole using some observational means, which I will describe, okay? Then we have the volume of the event horizon, okay? So this is just the mathematics, okay? You mustn't understand it. Then, so after doing the calculation, you will discover that stellar mass black holes are far more dense than supermassive black holes. I have not described what stellar mass black holes are and what supermassive black holes are. I'm going to describe them in few minutes. So what happens inside a black hole? How do we know what's going on inside a black hole? Unfortunately, we can never know what is going inside a black hole because in astronomy, most of the knowledge of celestial objects that we have are coming from electromagnetic waves or gravitational waves or neutrinos. But since black holes are not emitting anything, I mean, since light cannot escape a black hole, how can we possibly understand what is happening inside a black hole? So nobody knows, and no one will ever know what is happening inside a black hole. So most of the ideas, most of the things we know about black holes are coming from mathematics. That is why I showed you those gigantic equations when we started this lecture. When we started this lecture, I showed you some bunch of equations, some general theory or relativity, and I told you for you to understand a black hole very well, in a theoretical sense, you need to understand those mathematics, okay? So most of the ideas about black holes that we know today are from mathematics and from computer simulation. So now, there are two places in the universe that move faster than the speed of light. I said there are two places in the universe that move faster than the speed of light. Number one is the expansion of the universe. The expansion of the universe is faster than the speed of light. And then the speed at which space is dragged in a black hole is also happening at a rate faster than the speed of light. So 2 places. So space is dragged faster than the speed of light in a black hole and the expansion of the universe. But because we're talking about black holes, I want to let you to know that space is dragged faster than the speed of light inside a black hole. So types of black holes. Types of black holes. We have 4 different types of black holes. We have miniature black holes, or we can call them primordial black holes. We have stellar mass black holes. We have intermediate black holes, and we have supermassive black holes. So let us understand each of them properly. So primordial or miniature black holes. So during the formation of the universe, the first few hundred, the first time, the first millions of years or thousands of years the universe formed, okay, it wasn't as big as it is today. All of the matter that we know today are within it, okay? So the universe was dense, okay? Like we saw before, that it is density that causes these black holes. So hypothetically, we believe that the universe produced black holes. So these miniature black holes. So these miniature black holes can range from the mass that is called Planck's mass, okay? Remember I mentioned Planck's length before. I said Planck's length is the minimum size an object can get. Now, talking about Planck's mass. Planck's mass is the minimum mass an object can get, below which the definition of mass becomes very ambiguous. Okay, so the mass of these primordial black holes range from Planck's mass and above to a point which I will mention in the future. Okay, now, like I said before, this is hypothetical. We haven't confirmed it using observational means. So primordial black holes are hypothetical. We have no evidence of primordial black holes. Okay, so but assuming that we know about these primordial black holes, it can help us to explain the existence of dark matter. Dark matters are those kind of matters that do not interact with electromagnetic waves. Okay, they interact gravitationally, but not they don't interact with electromagnetic waves. So, and these primordial black holes can explain the supermassive black holes at the center of galaxies. I have not explained it yet, but these supermassive black holes are black holes that are located at the centers of galaxies that are very huge. And because they are huge, they take time to form, okay? So from the current model that we have nowadays, it can explain why these supermassive black holes form within a space of, less than 13.8 billion years, okay? They formed very early in the past, as big as they are. So if we are able to understand this primordial black hole, that means we may be able to explain the existence of these supermassive black holes. So we now have the second type of black hole we call the stellar mass black holes. In the stellar mass black holes, now I want you to understand that these stellar mass black holes were formed from stars that fuse hydrogen, helium, and other heavier elements. And by the end of their fusion, they had iron at the center, and iron does not fuse. However, iron absorbs energy and electrons. So because of that, the support system of the star, is gone. So the star collapses into a supernova. Okay, that becomes a black hole. So those stars that form black holes are stars that started out their lives with masses that are above 20 solar masses. Okay, so for these stellar mass black holes, okay, in fact, these stellar mass black holes are the remnants of the stars we have been studying in our series of stars. Okay, so the minimum mass is from 2 to 2.5 to 3 solar masses. Okay, now that is what we have been able to observe. Observationally, we have seen that stellar masses, for stellar mass black holes, their minimum mass is about around 2.5 to 3. So if tomorrow we are able to detect any black hole that is less than this mass, it means it falls into the range of primordial black holes. It falls into the range of primordial black holes. Do you understand? Remember, I told you about primordial black holes. Their mass range from the Planck's mass to now around this mass. So any mass that is less than this mass is a primordial black hole, and we haven't observed them yet. Most of the masses of black holes we observe today, the minimum mass is around this area, around this range, 2.5 to 3 solar masses. Now, so stellar mass black holes can have a mass as much maximum mass of 20 solar masses. Okay. Now, if you see a black hole at all that is bigger than these stellar mass black holes, they are from mergers. Maybe two stellar mass black holes combined together to form these huge black holes. Now, the event horizon ranges from 9 kilometers to 60 kilometers. Okay. Now, these 9 kilometers correspond to the minimum mass. Okay. While these 60 kilometers correspond to the maximum mass. So black holes with masses around 20 solar masses should have this kind of event horizon, this size of event horizon, okay, in terms of the diameter. So now stellar mass black holes have a higher average density than supermassive black holes. Now, in reality, we have just discovered a dozen of these stellar mass black holes, just a dozen of them, okay? But in theory, there are millions of these stellar black holes. You know, observing black holes is very hard because they do not emit anything. They do not emit radiation that we can measure. So that is why they are very hard to measure. So for the few dozen that we have discovered, how did we discover them? How did you discover them? So we have three methods of discovering these black holes. So we have three interactions with companion stars, and we have through gravitational microlensing, and we have gravitational waves. So I'm going to explain it with a simulation. I'm going to explain them with a simulation. So through interaction with companion star, so that is how we discovered the first star. The first black hole in the 1971. You know, I have mentioned this before. 85% of all the stars in our Milky Way galaxy exist in binary form and multiple star systems. So, I mean, 2 star systems orbiting each other, or 3 stars, or 4 stars. Do you understand? So, I mean, 85% of all the stars exist in this form, binary or multiple star systems. So you could have 2 stars. One could be very massive and one could be less massive, okay? Now, from what I've described about, you know, about stars with huge masses die quickly, okay? So why stars with less masses do not die quickly, okay? I've described that in the past, in our first lectures on stars. So when that happens, let me show you. I want to bring up this. I want to play this video. Okay. So you have these 2 stars. So this one is a black hole. It used to be a huge star like this, but it has died and a black hole is left at the center. Do you understand? So, but it is now, because of enormous gravitational influence it has, it is now beginning to steal matter from this star. It is beginning to steal matter from here. So you can see that it is stealing matter. So if we see this kind of arrangement in sky with our telescope, we knew that this is a black hole. It could be a neutron star, but in most cases, it could be a black hole. You can also see jets protruding from its pole. This jet is as a result of engulfing too much matter. It's engulfing too much matter. It is the same analogy as eating. Okay, if you are rushing food into your mouth, Okay, so you won't be able to take it off. So you kind of gush out, you kind of vomit some of them out. So that's exactly what is happening here. So it is engulfing a lot of matter. Because of that, it is ejecting it. It's a natural process. It's ejecting it through the pole. So we call it the jets. So anytime we see this arrangement with our telescope, we definitely know that this is a black hole. And that is how the first black hole was discovered in the 1971, called the Cygnus X1. So that is just interaction with a companion star. Okay, so we have other ones. If you're looking at your telescope and you see a group of stars behaving in a certain way around a particular region, okay, they come closer, they move faster from that region, and as they move away, they slow down, they come back again. Okay, you can even trace their orbit. They have an elliptical orbit around this region. So that is another way to pinpoint or to insinuate that maybe a black hole is there. A black hole is there. That is just one of them. Also notice that they were not torn apart. They were not torn apart. So now observe this one. Observe this one I'm going to show you right now. This star came very close to this black hole, and this black hole tear it apart. Okay, it tear it apart. Okay, so that is it. It tear the star into shreds. A black hole is very powerful, very, very powerful. We observed this in 2011, maybe, for several days. It came very close to the black hole, and the black hole teared so much apart, and and started to eat it up. So that is how we detect black holes, stellar mass black holes. Then another way of detecting stellar mass black holes is, imagine that you are observing this star. Look at your camera here, and you're observing this star, and the black hole kind of transverses through the path, the path of the light. So it is going to make this star to become brighter. So this black hole acts as a lens because it is massive. Massive object acts like that. We call that gravitational microlensing. So observe what is going to happen now. Observe what is going to happen now. It becomes brighter. So if that happens, so if you're observing, so another perspective, from our own perspective, our own telescope perspective, this is how it is going to be. Okay, so if you're doing this and you notice something like this, know that, oh, a black hole has just transversed. And here you have gravitational waves. So in this case, you have two black holes that are orbiting each other. As are orbiting each other, they are being decelerated. They decelerate. Okay. Now, I want to explain it a little bit, but when we talk about neutron stars, I will explain it in full. Okay. Now, on Earth, if you are driving your car and you immediately slam your brake, what happens? You experience friction. The friction dissipates the energy, the moving energy of the car into heat. Okay, that happens even with electrons. So if electrons come down in the energy level, they emit radiation. Okay, if they want to go up in the energy level, they absorb radiation. So for this system, this is space. Okay, space. Space is like a fabric. Okay, I have not fully described it, but I will still describe it. So here you have these two black holes orbiting each other. Okay, as they're orbiting each other, they are coming closer and closer. So now, as they're coming closer, what is going to make them to come closer? And that becomes, they're going to radiate gravitational waves. To make sense, they're going to radiate gravitational waves. This is part of Einstein's general theory of relativity, when you have two massive objects orbiting each other. So now we detect these gravitational waves through what we call interferometer. So As they're coming closer, they become faster, so the frequency increases until they merge. So this is the gravitational wave that we detect with the LIGO instrument. So this is one way of detecting gravitational waves. Sorry, of detecting stellar massive black holes. Stellar mass black holes. So then we have intermediate black holes. Now, black holes, stellar mass black holes can merge, okay? Just like the one we saw here in this simulation, when they merge, they become an intermediate black holes, IMBH. They become intermediate black holes. So these black hole mergers are called intermediate black holes. Their mass range from hundreds to hundreds of thousands, okay? So these intermediate black holes may play a crucial role in the formation of supermassive black holes. Okay, they might be part of the things that form supermassive black hole because we don't know yet what form these supermassive black holes. So we can also detect them the way we detect stellar mass black holes that we just described earlier on. So, like I said before, they can form through direct collapse of very massive stars in the early universe. Remember in the first lecture when I was describing star populations, population 3 stars. So I described population 3 stars as the first generation of stars, okay? They were more massive than any other stars that has ever been around in the universe, okay? Now, when some of them, theoretically, when some of them were collapsing, they collapsed directly into a black hole without exploding into a supernova, okay? So these intermediate black holes could form from these direct collapse of population 3 stars. Like I said before, black hole mergers. So intermediate black holes could be from black hole mergers. Then we have binary system of now when you have a binary system of stars, I have this. So we have binary system of stellar mass black hole plus a star. So let me show you that video again. So you have this star, you have this black hole, and you see this black hole is eating up matter from this massive star. As it is eating up this matter, it is getting bigger and bigger. So it could get more massive past the 20 solar mass mark for stellar mass black holes. So in that case, it could become an intermediate black hole. Now, how about supermassive black holes? So supermassive black holes are those black holes that are located at the centers of galaxies, okay? They are located, all the galaxies has black holes in them, okay? So they could range from 100,000 to tens of billions of solar masses, tens of billions, tens of billions of the mass of the sun. So you can imagine that is an insane, that's very, very insane mass. So now the event horizon can range from 29.5 million kilometers, could range from 29.5 million kilometers to about 2.95 trillion kilometers. So for this 29.5, it corresponds to these black holes here, and for these tens of billions of solar masses corresponds to this one here. Okay, because the more massive the black hole is, the bigger the event horizon. Now, for our Milky Way galaxy, our Milky Way galaxy has a supermassive black hole at the center. We call it the Sagittarius A. Okay, it has a mass of about 4 million solar masses. And how did we detect? How can we detect these supermassive black holes? So just like I described before, observing the motion of nearby stars near the center of the galaxy, of the galaxy. I've described that before. I even showed you the simulation. So if you see a group of stars, moving in a certain way, they move faster, slower, faster. When they come closer to a particular point, you should know that that should be maybe there's probably a black hole there. Then we have jets and relativistic beams from AGN. We call this active galactic nuclei. So here's a simulation showing that. So you see these stars behaving in a particular way near the center of this just near here. They're behaving in a particular way. So just know that there could be a black hole at the center of a. So if you look at the center of most galaxies, that is how stars behave. So we have the AGN, we call it the active galactic nuclei. You have this galaxy engulfing matter at a very high rate. And because of that, it is ejecting some of this matter out, just like what we saw from these binary star systems of a black hole and another main sequence star. By the way, that's a sound in this video, but you can't hear it because of the zoom. The zoom does not allow that. So when we see this with our telescope, we know that this is a black hole. In fact, it is this black hole that powers these jets. This is very massive. AGNs have the biggest black holes. I mean, their black holes are bigger. Their black holes are bigger because they're always engulfing matter and getting bigger. So that is why. So let us compare our sun, our Earth, to black holes, so that you can have a better understanding of how massive black holes are. So here is our Earth, here is our sun, and here is the Sagittarius A, the black hole at our Milky Way galaxy, and here are all the black holes in our epoch. These black holes are mostly in our epoch. So we have this Messier 106, AGN 5543. So black holes are the centers of so many centers of galaxies. So Hercules A, M87, NG3842, AGC 1600, OJ 287. And here you have the comparison of OJ 287. If you compare it with the size of our solar system, you can see that it is much bigger than us. It can just swallow our solar system and nothing will happen, as if nothing would never existed. So we have other ones. We have other ones that are even bigger than it. Then we have this one, NGCU 6166. I have Ton 618. Then look at Ton 618 compared to the distance from the sun to the Earth. So you can see how big it is. This black hole is so massive, so insanely massive. And then you have another galaxy, another black hole that called Phoenix A, that is bigger than this 6 Ton 618. So this Hercules is the biggest black hole. This one here is the biggest black hole that we have ever detected. It's at the center of this is the orbit of Neptune. It is at the center of our galaxy. So black holes and space-time, let us use black holes to understand space-time. Because Albert Einstein came up with his theory to explain space-time. Now, according to Isaac Newton, space is rigid, okay? Space is rigid, time is the same everywhere, and gravity emanates from mass, okay? He said that gravity is coming from mass. Do you understand? That is his own idea of gravity. It is from mass, okay? Now, his theory pretty much works today. It pretty much works. Do you understand? But it could not explain a lot of things, example, black holes. So Einstein came on board and added some knowledge on top of Isaac, ideas. Albert Einstein said, space is not rigid. Rather, space is like a fabric, okay? space is like a material, and time runs at different rates. In fact, what he called gravity is a dent in the space-time fabric. Let me show you this simulation. So here you have the sun, and here you have space, call it space-time. Okay, so you see how this massive object like the sun and the earth and the moon are causing dents, and the earth is moving in the dent of the sun. So this dent, according to Albert Einstein, is called gravity. It is what causes gravity. Do you understand? So if you are in a region that is dented, you experience a different rate of time flow than a place that is not dented. Do you understand? So Albert Einstein said that space and time are intertwined into a fabric called the space-time fabric, okay, space-time continuum. So, and gravity is the curvature of the space-time fabric. So here is another simulation. I've showed it before. Here you have two black holes, okay, radiating gravitational waves as they are coming closer to each other. So look at how they are bending space. Look at how they are causing dents. So an infinite dent. So they are coming closer and closer, and it is faster. Look at this. Look at this picture here. As they're coming closer, they are radiating more and more gravitational waves. And at a point, they combine. So I just want to show you some things about space-time fabric. So to understand Albert Einstein's idea, so here is a mountain and here is a valley. So this is the tallest mountain in the world, Mountain Everest, okay, in Asia. So imagine that we are two scientists, we synchronize two clocks, and you took one on top of this mountain while I stayed back on Earth. After a very long period of time, don't ask me what I mean by long period of time. It could be millions of years. It could be some few days. But after a very long period of time, we would notice that the clocks are out of alignment. They are no longer synchronized like when we started. And what is causing that? The reason for that is because gravity runs at different rates. The gravity here is less than the gravity here. You understand? And gravity affects time. Where gravity is more, time runs slowly. Where gravity runs slowly, time runs faster. Mean more action, okay? Understand it, more action, more chemical reaction, more natural processes, more processes of anything in a place where gravity is less. Even clocks. So for Earth, the gravitational field of the Earth is very less. So we don't usually notice these things. Do you understand? We don't usually notice these things. But assuming that we are in a place of enormous gravitational influence, it is very much pronounced. So here is a man standing, okay? Here is a ruler. So in his leg, we can put a clock in his leg, put a clock here, put a clock here. So if this man is standing on Earth, okay? If this man is standing on Earth, okay? With time, these clocks are going to run out of order, okay, after a long period of time. Although you don't stand that long to notice that, but assuming we are in a region of enormous gravitational influence, you would notice that the time that is running here is lower than the time here and to the time here. So because as you're moving out, as the altitude is increasing, the gravity is decreasing. So now, taking this idea into account, now here is a movie, the Interstellar movie. In this movie, some group of space explorers were sent to a black hole. Okay, so to investigate certain things. It's been a long time I watched the movie, so now they discovered there was a planet around this black hole that was orbiting this black hole. So they decided to stop by it. But when they got around the orbit of that planet, okay, we call it Miller's planet, okay, some of them went down, descended into the planet, while others remained in the spaceship. Okay, now they spent 3 years. They spent 3 years on that planet. By the time those ground crew came up to the space shuttle, 25 years has passed for those that remained. So those that remained here became older. So that is exactly what is happening. We call this gravitational time dilation. It's a time dilation caused by gravity. Okay, so that is exactly because of the normal gravitational from this black hole. So tidal forces. What are tidal forces? Okay, because of the enormous gravitational pull, because of the enormous gravitational influence of a black hole, if you are falling into a black hole, you will be spaghettified. And what is causing this? We call it, it's a tidal effect anyway. What is causing this is because of the differences in gravity. Like I told you before, the gravity here is higher than the gravity here, if you're on Earth. Do you understand? Now, if you are falling into a black hole with your legs on, okay, your legs is facing the black hole compared to your head. So the force of gravity here, in fact, the force of gravity at every inch of your body is different. It is so enormous that it can tear you apart, and that results into spaghettification. Now, for a stellar mass black holes, you will experience spaghettification. Let me play this video. Okay. You experience spaghettification even before you get into the event horizon. But for a supermassive black hole, you will not be spaghettified if you are outside the event horizon. So you could just fall in gently into the black hole, but you experience the spaghettification right inside the event horizon. However, we won't be able to see that because light cannot escape the event horizon. So that's a simulation of the event horizon. So now at the event horizon, time stops. Remember, the event horizon is where we can no longer see light anymore. So imagine that we observe an object falling into a black hole. We observe an object falling into a black hole. Okay? As object is falling in, as it is falling in, every unit of length or every unit of space, it moves closer to the event horizon. Gravity increases enormously. Remember, so it takes more energy for that photon to escape. So, and also understanding that space is being stretched. So by the time the photon is going to make it out, it is going to be stretched. So if the photon started its life, the local wavelength is white, by the time it reaches you, it becomes yellow, and so on and so forth. So as we observe this object fall into a black hole, we see the time stop, assuming it is carrying a clock. As soon as it crosses this event horizon, the time stops. Okay, so and then it freezes. the object freezes. And if you continue observing it, it becomes redder and redder and redder until you will see it no more. Because right at that point, that photon needs a speed larger than the speed of light to escape, which is not possible. So right at the event horizon, time stops. Time becomes 0 for the outside observer. Time stops flowing for the outside observer, not for the inside observer. The inside observer will continue falling. Okay, if it is possible to even make it out, it can even tell you some series of events it witnessed. Now, we say that a black hole does not emit anything. It does not emit electromagnetic waves. And you know, we use electromagnetic waves emanating from objects to measure their temperatures. So if a black hole is sucking everything, all electromagnetic waves, so does it mean that it does not have temperature? Or does a black hole have a temperature? That was what puzzled scientists in the earlier on, in the times of Stephen Hawking. So Stephen Hawking came on the board and answered it. And here is how it works. In reality, we have what we call pair production and pair annihilation. We have what we call visual particles. These particles, they pop out and annihilate themselves. However, these particles are not real particles. They do not obey the laws of physics, okay? So they're called virtual particles. They pop out, okay, and annihilate themselves. The time at which they pop out and annihilate themselves are so small that it is even hard to measure their existence. However, if this were to happen close to the event horizon, look at the black hole, and this is the event horizon. You know, event horizon has enormous gravity. Like a black hole, it has enormous gravity. When that happens, the gravity, the black hole, you know, can steal away the other pair. Okay, the force of gravity can, you know, can separate, okay, the other pair. Okay, so here could be a negative mass and here will be a positive mass. So when they combine, it becomes 0. So when this happens, this yellow, which is the positive mass, will escape the black hole and become a real particle. While this one falls in negative mass to subtract a mass from the black hole. So therefore, if a black hole experiences this, it means that with time, it is going to evaporate. And however, it is radiating. So it means the black hole is going to get smaller and smaller if this would happen. So because of this negative mass subtracting from the overall mass of the black hole. So we call this, so this one is the one that we can detect. We call this Hawking radiation. And this can give the signature of the temperature of a black hole. Now, it is very hard to detect these Hawking radiation. It is very hard to detect them because they are very faint. Okay? Black holes are very huge. Now, according to the mathematics, the bigger the black hole, the lesser the rate of this event, of this Hawking radiation. Okay, so it means for this massive black hole that we have in the universe, the rate of the Hawking radiation will be much less. We will not have enough to detect them from the ground-based space telescope. So there are so many proposals to create a black hole as a Large Hadron Collider, a miniature black hole that could evaporate so fast. And that has caused a public outcry that this black hole could, you know, eat Earth. You know, there could be some mistakes. It could eventually run out and start to, you know, consuming and sucking everything and even consume Earth. However, from the physicists, they said that it will be manufactured and it will just, you know, radiate away in a fraction of a second. So that danger of eating Earth could be avoided. However, you know, the public has not won the trust. So this is Stephen Hawking's idea. Although we haven't proved it yet, it's actually a theory. But assuming that we were able to prove it, Stephen Hawking would have gotten a Nobel Prize. However, he is dead, and he died in 2018, and he won't be able to get a Nobel Prize even if we prove it in the future. We don't give Nobel Prize to dead scientists, but he did an enormous work in astrophysics. So the smaller the black hole, the higher the Hawking radiation and vice versa. So in 2019, the first image of a black hole was taken. These are black holes at the centers of galaxies. So you can see it. And just this year, 2024, this image of a black hole was taken, showing its magnetic fields. Where does the magnetic field of a black hole come from? Unlike solid objects like stars, planets, neutron stars, and even white dwarfs, their black holes are coming from the surface, from the core to the surface of those objects. But for a black hole, does not emit anything. So how come it has magnetic fields? Now, the black holes that have magnetic fields are black holes that have accretion disk. So this is an accretion disk. An accretion disk are just matter that are being swallowed by the black hole. So they do not fall into the black hole immediately. They orbit the black hole, for a very long period of time until they get swallowed up. So as they are moving around the black hole, it is not a laminar flow. So they collide with themselves. They are moving at a very high speed, relativistic speed. So they collide with themselves and they generate that is friction. They generate heat. Okay, they become charged particles. Now, from the idea of electromagnetic waves, electromagnetic theory, when charged particles are in motion, they generate magnetic fields. So the magnetic field of black holes are coming from this accretion disk and not from the black hole itself. So that will bring me to the end of this lecture. So next time, I'm going to talk about neutron stars.